Newton's method. Newton's method is a way of estimating the roots of an equation. So this is estimates the roots. Roots of an equation. Basically any equation, although it has to be something that you know how to take the derivative of, so it can't be too wild. But the roots, of course, means, roots means x values where f of x equals 0. So on a graph, this would be the x-intercepts, but you don't have to think of them in terms of the graph. Really, this is useful in many situations where people don't necessarily care about the graph. X values where f of x equals 0. All right, the example we were talking about last time, I had a picture to look at. It was the function that we were using was f of x equal x squared minus 2. And the reason I was focused on that particular function is because we already know that the roots of this one are plus or minus square root of 2, right? Because if you set that thing, x squared minus 2, if you set this equal to 0 and solve for x, what you get is the square root of 2 and negative square root of 2. That's what these x-intercepts are, right? This is root 2. And I suppose, these numbers, 1 and 2, go something like that. Root 2 is something like 1.4, so it would be in between 1 and 2. All right. The strategy, I hope you remember, is you begin with a guess. Which you can just pull out of nowhere, or you can try to make an educated guess by looking at the graph. And that guess we call x1. That's the first approximation. And the guess is probably not very close to the true answer because it's just a guess. But the strategy is, let's say in this case I choose x1 to be 1.5, just because I guess, looking at the graph, this is somewhere in between 1 and 2. So 1.5 doesn't seem like such a bad idea, right? The strategy, the idea is you go to this point, you look on the graph at that point, you draw the tangent line to the curve, which in this example would look, something like that maybe. And then you find the x-intercept of the tangent line. And that will be quite close to the actual root. On my picture, actually, they're almost indistinguishable. I'll draw this in blue so you can see a little better. You draw the tangent line here, and then you pick the x-intercept. And that we call x2. That's our second approximation. On this picture, the x2 is actually already very close to the true square root of 2. But if that's not close enough for you, you can just continue the process. Right at that point, at x2, I'm not going to try to do this, but you would draw the tangent line right there. I'm zoomed in, so my dot is giant. And then, draw another tangent line, take its x-intercept, and it'll be even closer to the true value of the square root of 2. This is the idea. So let me just say, you begin with a guess, x1, and then you draw the tangent line at that guess point, x1, which is the blue line that I drew in the picture. And then you say x2 is the x-intercept of that tangent line. Of that tangent line. All right, and x2 is even closer to the root that you're looking for. And then if you want it to get even closer, you just do it again. And you continue, do it as many times as you want. All right, this is Newton's method. Now, it sounds like a decent idea, but if you're just joining us, it may sound overly complicated. Not overly complicated, but it seems complicated to draw those tangent lines every time and then continually find the x-intercept. But lucky for us, there is a very simple formula for these x-intercepts. And we talked about this at the end last time. I don't know if you remember, but I will refresh your memory of the formula. An easy formula. All this, what looks like on the surface kind of complicated geometry, it turns out boils down to an easy easily remembered formula. It's this. x2 is x1 minus that fraction, f of x1 divided by f prime of x1. All right? You got to go through a bunch of geometry to get there, but eventually everything ends up sort of simplifying down, and you end up with this very nice looking simple formula for x2 in terms of x1. Now, if you want to go to x3, you just do the same formula using x2 in place of x1. So I'm going to say generally xn, actually I'm going to write, I think this is where I ended up last time. xn plus 1 is xn minus f of xn over f of f prime of xn. Sorry. All right, and this is the formula for Newton's method. This is the one to remember. All right. Like I said, this isn't going to be on our test this week, but eventually, this is the formula to use to do Newton's method. This tells you how to get the next guess starting from the previous one. All right. So today I just want to do some examples, and I got some for you all to try. It's a pretty, not terribly complicated formula once you get down to it. The idea behind it is a little complicated, but when it comes to actually doing examples, it's pretty straightforward. Okay, so let's just actually work it out for this example that I drew the picture of before. So I want to try to estimate the square root of 2. So if this were like a homework problem or a test question, I would say, please, I always say please on the test and the quiz, please estimate the square root of 2 using Newton's method, Newt's meth, with the first guess of x1 equals 1.5, say. Usually, like for the sake of our tests, I will tell you how to choose the first guess just so that everybody in theory will end up with the same answer. Although if you start with a slightly different guess, your answers will all be slightly different, but they will still eventually get very close to the square root of 2. All right, anyway, first of all, you need to choose the appropriate function. And this is sometimes tricky, but in this example, I already told you what function that we're using. It will be x squared minus 2 equals 0. All right? This is the function whose root is the square root of 2, and also negative the square root of 2. You may be wondering, this thing actually has 2 roots, but Newton's method apparently will just give you closer and closer values to one of the roots. Which root will it be, the positive square root of 2 or the negative square root of 2? Well, it depends on which guess you choose. If you start with guess 1.5, eventually these lines will accumulate and converge around the square root of 2. Whereas if you started with some guess over here, negative 2 or something, and did the Newton's method, eventually those lines would accumulate to the negative square root of 2. Anyway, okay, so this is the function, f of x equals x squared minus 2, all right? And now we basically have all the ingredients to just work this out completely, right? My first guess is x1 equals 1.5. And the formula says x2, well, before I write the formula does involve the derivative, right? It had an f prime in there. So we might as well find the derivative. In this case, this is easy. What's the derivative? 2x, yes. You are well prepared for the test. If you don't know that, you are not prepared for the test. If you do know that, you might be prepared for the test. Okay, let's just plug it all in. So I'm just going to sort of make a big list here. x1 is not very accurate, but that's our first guess. x2 is, I'll write the formula first, x1 minus f of x1 over f prime of x1, right? And you plug everything in. This is 1.5 minus, okay, f of 1.5 is 1.5 squared minus 2, right? And then divided by 2 times 1.5. I plugged into the f and to the f prime. Unfortunately, you basically need to do your calculator immediately in this kind of problem. Usually, you won't really be able to simplify much of anything without using your calculator. Anyway, I typed all of those numbers into my calculator, and I got 1.41666 repeating like that. All right. This is pretty good. The actual value, maybe I'll say parenthetically, actually, square root of 2 is 1.414213, etc. All right. So after my first kind of run through the Newton's method, this is x2. It's already pretty good. I mean, I started off at 1.5, which was kind of close, I guess. This is quite a bit better. All right. Let's do one more. Let's do x3 and see what we get. So this time, I am going to just do this same setup again, but I use this 1.416 repeating instead of 1.5. So it's going to be 1.416. I'll put the little bar there. You know what I mean by that, right? Up here, 1.416 with the bar minus 2 divided by 2 times 1.416 repeating. Right? I plugged it in again. And I did my calculator on this. This one is, you ready for this? 1.414215. That's really quite close to the actual decimal value of the square root of 2 up here, right? And I mean, to me, this is sort of remarkably accurate. I only had to do it twice, but I'm already matching the actual square root of 2 to like 5 decimal places, right? That's really quite accurate. This is how you do Newton's method. Once you know the formula, really there's not much to it. You plug it in, and it works great. Any questions about that one? All right, let's just try a similar one. And then, like I said, I got some for you to try. They don't really get any harder than this. You know, you just you have to set it up properly, but then it's just a matter of running it through your calculator a few times. Let's try estimate. How about the 10th root of 10? No, the 10th root of 100. How do you like that? With first guess, just so that we're all getting the same answer here, of x1 equals 2. All right. First of all, can you do something with the 10th root of 100? Isn't that like 10 or something? The answer is no, it's not. It's not anything really. It looks like maybe you should be able to simplify that, but you can't. Is this a decent guess? If the 10th root of 100 really equal 2, that would mean 2 to the 10 equals 100. That's actually far too high. 2 to the 10 is 1024, I happen to know, which is a lot more than 100. So the true value of a 10th root of 100 is less than 2. But it is more than 1, right? Because 1 to the 10th is only 1. So it's got to be between 1 and 2. But anyway, let's try x equal 2. All right?
Same function as the example.
Yeah, we got to talk about the function. What function should we use? Now, in the previous example, I was looking for the square root of 2 specifically, and that's why I used this function, x squared minus 2, because the square root of 2 is the number which makes this function equal 0, all right? In our example, it's got to be a different function. So what function? You need to invent a function so we need some f where f of the 10th root of 100 equals 0, right? You want to think of such a function? It is kind of similar to the one we did before. I wanted the square root of 2 before, so I used 2 squared minus 2 as my function. Because if you put the square root of 2 in here, you will actually get 0. Any ideas? How can I make it so that it's the 10th root of 100? Yeah.
X to the 10th minus 100.
Yeah, he said x to the 10 minus 100. I like that. F of x equals x to the 10 minus 100. Right? Basically, if you have a root, some kind of weird root here, you want to use x to some power minus something as your function. In this case, x to the 10 minus 100. All right. And then, you know, I use my first guess just because I said so, x1 equals 2, and we should be able to just sort of plug and chug it at this point, all right? So I'm going to do, okay, x1 is 2, then sorry, can I just say, first of all, let's do the derivative, right? Because this is going to be involved when I, you know, eventually want to do the plug and chugging. The derivative here is always going to be easy if you're doing one of these kinds of functions. It's just 10x to the 9, right? And if you like, you can even simplify a little bit. You have my formula eventually will involve things that look like, sorry, that's on the bottom. It's f of x over f prime of x, right? This is what you see in the formula. And that, in this example, you can even simplify that. You could have done this in the previous example too. This is x to the 10 minus 100 over 10x to the 9, which if you just sort of divide each of those things and subtract the exponents, if you like. It's not really necessary to do this, but it's 1 over 10x minus, isn't it 10 over x to the 9, right? If you split this fraction up across the numerator, x to the 10 over 10x to the 9 simplifies to that. And then 100 over 10x to the 9 simplifies to that, if you want. Sorry, this x should be up top. I saw that. Sorry about that. X to the 10 over 10x to the 9. All the x's cancel except one left over on top. All right, I don't know if it's worth doing that simplification. But anyway, I'm ready to plug into my calculator. This is 2. So x2 is going to be 2 minus f of 2 over f prime of 2, right? And then you plug it all in. So this is 2 minus, and you could, this is why I did this right here. You can just use that right here if you want. Or you could just plug in as a fraction. It doesn't matter. Maybe I'll just use the original thing. Right, like that. And you just type that business into your calculator. I don't know if anybody has a philosophical objection to this. These problems are about approximating values by hand, but I'm more or less immediately using my calculator. Do you feel like that's sort of a cheat? The whole point of this is to find, say, the square root of 2 by hand. Shouldn't I just not ever use my calculator if I want to do it by hand? You gotta sort of put yourself in the shoes of Isaac Newton or somebody trying to do this back in the day. Without a calculator, you basically cannot compute this number, right? But you could do all of these numbers because in these steps, all I'm doing is powers and multiplying and stuff like that, all right? So this is, at least in theory, possible for me to do by hand. I know exactly how I would do it. I wouldn't really want to do it, but this is something any of us could do if you had enough time. Whereas doing the 10th root of 100 is something that you wouldn't even know how to do at all. So that's the difference. I am using my calculator, but only to do these simple multiplications and adding and subtracting. Anyway, I typed this into my calculator. I got 1.819. And maybe actually I want to show you a little life hack about plugging these things into your calculator, because we're going to plug this number into the calculator again. You don't want to round any intermediate steps though, because each different approximation is actually going to be so close together that if you round off, say, to the first 3 decimal places, that's going to mess up your next answer because they are more precise than that. So here's my little suggestion. I am going to type this in. I got my calculator here. It's gone now. What did it say? 2 minus, and then I got a fraction of 2 to the 10. Can you see where I'm typing? It's down in the box down there. And then minus 100, right? Divided by, make sure I get my parentheses right, 10 times 2 to the 9. All right, this is what I get. And that's that number I said before, 1.819, etc. But like I said, when you're doing this, if you want to get good answers, you can never round this number. So for my next step, I'm going to do the same thing again, only that thing that I just typed in, I'm going to type the same thing, but instead of those 2's, I use this number, 1.819. So I'm going to use the little ants button a lot. Oh, you can't see it. It's off the bottom of the screens up there. But I'm going to hit the little ants. That's my answer button. Minus. Any of your TI calculators will have this. So I go answer to the 10 minus 100 close parentheses divided by 10 times the answer to the 9, like that. And I got 1.6833, all right? You will be able to know if you messed it up or not. Like if that number changes wildly, then you probably typed it in wrong, your thing that you're calculating, all right? You should expect these answers to look very similar to one another from one step to the next. And then you just do that whole thing again. I'll do one more. Answer minus, this is kind of boring to watch somebody do in public, but this thing minus 100 divided by 10 times the answer to the 9. And I got 1.607. All right, I guess this now is x4, right? The first one was x1. That was my guess, and then I just did 3 more. In this case, I did a few more here ahead of time. I'll just tell you what I got. So that was x4, was 1.607, etc. I did x5, I got 1.586229. x6, I did these ahead of time. I got 1.5848982245. I'm just going out to x7 just to demonstrate something here. 1.5848933193. All right. You can see these are becoming increasingly similar to one another as we continue down the list. All right. That's a signal that you probably are doing it right. If you are doing this procedure step by step and you end up getting really like wildly different answers every time, then you probably messed up the calculator. All right. Sometimes the book might say to in the homework problems or something. Sometimes they say estimate to within the nearest thousandth or something like that. These answers, because we're using Newton's method, we expect them to get more and more accurate from step to step. But how do you know when the answer is accurate enough? Like if I said, I need it to be accurate within the nearest thousandth, how do you know when the answer is that accurate? Well, you can tell when the digits, the thousandth would be this digit, right? That's the thousandths digit. How do you know when that digit is accurate? Well, when you've done so many steps that digit is just going to be the same every time from now on. So actually, I can tell that this 6, when I first wrote the 6, I wasn't sure if that was accurate. But here it became a 4, which means I guess the 6 is probably not accurate. But then here it stayed a 4, and you can tell that this is going to stay a 4 forever. So after this step right here, when this 4 repeated itself, I can be confident that the number to the nearest thousandth is 1.584, right? So if they are asking you to get a certain amount of accuracy, you just have to do enough steps until you see that the answers are correct in those positions, all right? The answers don't keep on changing. All right, any questions about that? Let's try some examples. I got 2 examples for you to try. So the first one, the second one will look quite different, but is actually easier. I would like to estimate the cube root of 9 to the nearest thousandth. You will want to use your calculator for this, and I hope you have a calculator with an answer button. If not, do your best. The one you just saw me using is the Desmos Scientific Calculator, which is a free app, so you can get that if you're lacking. This one I'm not going to tell you an initial guess But if you think about it, you should feel like you have, there's a natural guess to use here. Think of what number you think is kind of close to the cube root of 9. Anyway, and here, I got another one to try. Second one just says find a root of this function in the interval -4 to 0. And I said just go out to x3, the third estimate. That one also I'm not going to tell you an initial guess. Again, there's one that kind of makes sense to use. All right, I hope you don't mind the plugging into your calculators. I think it's kind of boring in my experience, though. A lot of people like the security they feel when they hit those buttons. It makes you feel good. Go for it. Oh, yeah.
I still not sure.
The cube root of 9. So what about, I happen to know the cube root is
Don't worry about it. You sit there and relax. She'll take the two.
So you got cube root 8. So the cube root of 9.
So basically, like, you're just doing that, like, looking at this closest to
Yes, because it's 9. So like, it's actually
I have to say, like, I'll be really
I'm going to start doing the first one over here. All right, let's talk about these. So the first one, it looked like pretty much everybody was doing great. The function you want to use is x cubed minus 9. And then the guess you should use, in this case, I said there was a kind of a reasonable guess. 2, that's because the cube root of 8 is 2. And so I would expect the cube root of 9 is something kind of close to 2. All right. And if you did this, eventually you should get, I don't think you need to watch me do all the numbers here, but you should get something like 2.0800 something. I hope that you got those kinds of digits. If you got different digits than that, you probably typed something in wrong at some point, which, this is not a class about typing things into your calculator, so I'm not too worried if you just make a little mistake like that. I hope everybody's with it on the procedure, right? Okay, and then the other one was a kind of differently phrased, but find a root of this function on this interval. Of course, the function, I just told you the function. So for that one, you don't have to think about what function am I going to use. And I also told you an interval. This should kind of inform the guess, I guess. That's the only other ingredient of this one. So for the second one, you're going to use this as the function. F of x is 4x cubed minus 5x squared plus 10. And then you want, I said, find a root on that interval, on the interval minus 4 to 0. Any thoughts about our first guess? Start with x1. What did you pick as a guess? This is a complicated function, so there's no real good way to just look at the formula and come up with a guess. What do you think? Negative 1? Why'd you choose that?
Because it would, if you plugged in negative 1, it would make fx equal to 1, which is close to 0.
Yeah, okay. That's not so bad. Actually, I wasn't expecting you to think that hard about it. I don't know what anybody else decided, but I would have just started with x1 equals negative 2, which is in the middle of this interval, and then go, start from there. Although probably negative 1, it's not really going to matter what starting point you pick, because you will end up converging to the true value of the root, whatever it is anyway. I would have chosen this because this is just the middle of the interval. Right. This is why you may have used some kind of root finding procedure on your calculator before. I don't know if your calculator has some kind of generic equation solver, but a lot of times those things require you to give it an interval. And that's why, really, it's because they're using something vaguely like Newton's method to solve the equation, and they need some kind of a starting point to start the approximations going. All right, I would have used negative 2. But anyway, given that choice, the whole rest of the procedure is the same old thing. You take the derivative here, you get 12x squared minus 10x, and then you plug everything in. So x2 in this case would have been negative 2 if you start with negative 2, minus f of negative 2 would be 12 times minus 2 squared minus 10 times minus 2. Sorry, that's the bottom. I'll just move that down a little. Whoa, I'm losing it. And then the top was 4 times x cubed minus 5 times x squared plus 10, like that. Come on, it's happening. All right, so that would have been x2, whatever that is. I didn't type this into my calculator. And then x3. I said specifically just to go to x3, so plug it in once more to your calculator. All right. This is Newton's method. Not all that much more to say about it. Anybody have any questions? Newton's method. So there is one last thing I want to say about Newton's method is, unfortunately, sometimes the Newton's method fails It's true. I want to just, I don't want to talk too much about this, but I want to just give you a sense of why this happens. Newton's method is maybe one of the first sophisticated root finding procedures that was developed using calculus. There are many other methods for trying to find roots of equations, and actually we have, this is the basic beginnings of an area of mathematics called numerical analysis, which we have, if you're a math major, we have a course on numerical analysis, which is all about different kinds of procedures for solving problems in this way, where you don't really get the exact answer, but you can get super accurate approximations that can be so accurate that it doesn't matter if it's the exact answer or not. Anyway, sometimes Newton's method fails. There are basically three ways that this can happen, or at least three ways that I will say. First way it can fail is if f prime of x1 is 0. That's because the formula for x2 was x1 minus f of x1 over f prime of x1. And you can tell there's going to be a problem if that denominator is 0, right? If f prime of x1 is 0, then you just can't there is no x2 in that case. And actually what this means, if you're, say, looking at the picture, it would mean something like this. If you're looking for, if you're looking for this root right here, but for some reason you chose x1 to be that point, then if you're doing the Newton's method on the picture, you would go up to the curve at that point, draw the tangent line, and find its x-intercept. But this tangent line has no x-intercept, and you're just stuck. There is no way to proceed from there. And so, in this case, Newton's method doesn't work. Although in the real world, this is not such a big deal, because if you really needed to use Newton's method in a case like this, you would just change your guess by a little bit, and then the derivative wouldn't be 0 anymore at that point. Okay, so this is a problem. Come on now. All right, so I will say if f prime of x1 equals 0, we can't continue. But we could just adjust our guess so that f prime of x1 is not 0 anymore, right? The x1 is something that I chose myself. So this is not like an insurmountable mathematical problem. It just means I made a bad choice of the x1. And if you really needed to know the answer, you could just choose a different value for x1 where the derivative is not 0. So this is a failure case, but it's not really much of a big deal. A more big deal, this is a more substantial case which really doesn't have a great kind of workaround, is something like, I'm going to try to do something like this. And let's say I'm trying to estimate this value right here. I'm looking for this root, but for some reason my guess, I'm not able to come up with a great guess, and let's say for some reason I choose x1 to be that over there. All right. What happens now if we do the procedure where I draw the tangent line and all that? So if I draw the tangent line, I'll make it blue again. I go up to this point here, I draw the tangent line, and it makes my x2 down here, the x-intercept of the tangent line, right? This time it ends up being down there, which is even farther away from the true value of the root, right? What if, typically if your estimation is not good enough yet, you do the procedure again. What if I did it again starting at x2? Well, now I would go up to the tangent line there, draw the tangent line again, and now it's like this, right? It's kind of bogus picture, but I hope you get the idea of what I'm saying. Now it's even worse. In this example, actually, because of the weird shape of this curve, the Newton's method estimations get worse and worse every time. They are not getting closer to the true root. Actually, they're just going to go off to the right side of this picture forever. So here, the xn do not approach the root. This is a real problem. which has, there isn't really an obvious way to get around this in this example, other than your first guess was bad, right? You should not have started at this value over here. If you started somewhere a lot closer, then that wouldn't happen. It wouldn't go off to the right forever. It would just converge to this value. But anyway, in this case, we say Newton's method does not converge. That's the fancy language for this. Newton's method does not converge. In this example, right? That's in this particular case. It can happen sometimes that the Newton's method, those numbers don't actually approach anything. They just go out to infinity. Like in this example, they will go out to infinity. Or they might go back out to minus infinity. All right? In that case, you should try to use a different guess, although it still might not work if you choose a different guess. This is worse than, in this example, basically, in this first one, remember the problem was that the derivative is 0 here. Basically, any other guess would have worked here. We just chose like a uniquely bad guess right there. Whereas here, even on any other value all around here, they would all have the same kind of failure behavior. So Newton's method is not foolproof. It was, in its time, kind of revolutionary and super accurate in a way that other methods, at the time, there were not better ways to do this. Nowadays, we have much more sophisticated things, which, like I said, you can learn about in a numerical analysis class. We don't need to get into that anymore. All right, that's all I wanted to say about Newton's method. Any thoughts about that? It's a great, fairly simple root finding procedure. I think, in my opinion, it's kind of a miracle that it works. That it's a complicated idea, drawing these tangent lines and doing the intercepts, but it all boils down to a very, very simple formula, which I think is pretty great. All right, that's all about Newton's method. We got about 20 minutes left. I think that's enough time to get started on the next section. And would you believe it? Newton's method is the last section about the derivative. Can you believe it? We are done talking about the derivative, kind of. The derivative will be sort of lurking in the background of everything that we say for the rest of the semester. But for now, we're going to talk about the antiderivative. Remember that? Maybe. The antiderivative. Also known as the integral, which will be the major topic for the rest of the course, which is, a few more weeks. The antiderivative. Usually if you ask a calculus student, after the end of the course, what was that class even about? They will probably say, calculus is about derivatives and integrals, which is another word for the antiderivative. So this is kind of a starting of a new leaf or something. If you got tired of doing the derivative over and over again, maybe this is a chance for a fresh start. It's not all that different though, but it is pretty different. So the antiderivative, the idea is sort of doing the derivative backwards or undoing the derivative. That's what it's called, the antiderivative. Here's the idea. Given some function f of x, an antiderivative, we talk all the time about take the derivative of this or that function. Now we're going to talk about also take the antiderivative of this or that function. An antiderivative of f is some other function which I will write as big F, which with this property. So what makes it the antiderivative is the derivative of the big F is the little f. All right? So this, what I just wrote, if you were to read that formula in words, you would probably say that the derivative of the big F is the little f, right? This is the same, this means the same as, to say it another way around, it means the antiderivative of the little f is the big F, all right? If you say the derivative of the big one, the big F is the little f, that's the same as saying the antiderivative of the little f is the big F. All right. So the antiderivative is kind of the opposite of the derivative or something. the other way of saying it. This is what the kids these days call a fact family. Have you heard of fact families? This is like a thing that when kids learn math. Every so often I talk to my kids and I ask them, like, what are you doing in math these days? And my kid, like, when she was in like second grade, she said, oh yeah, in math we're doing fact families. And I had never heard of that. So I said, what's a fact family? And she's like, oh, a fact family is like, 1 plus 2 equals 3. And also, 3 minus 1 equals 2. That's a fact family. These are two true facts that kind of mean the same thing. They're just rearranged somehow. You're saying the same thing in two different ways. All right? This is a fact family here. When I say the derivative of one thing is the other thing, that's the same as saying the antiderivative of the other thing is the first thing. All right? That's a fact family. Now you know what a fact family is. All right? So, for example, the derivative, everybody knows, the derivative of x squared is 2x. To say it the other way around, it means, I will say an antiderivative. I'm not going to say the antiderivative for reasons that I will mention in a moment. An antiderivative of 2x is x squared, right? It's the other way around. If the derivative of x squared is 2x, that means the antiderivative of 2x is x squared. Now, I said an here rather than the. That's because, unlike the derivative, there's actually more than one possible antiderivative from a given function. An antiderivative of 2x is x squared. That's because the derivative of x squared is 2x. But also, another antiderivative of 2x is something like x squared plus 1. Would you agree that the derivative of x squared plus 1 is also 2x, right? The derivative of x squared is 2x, but the derivative of x squared plus 1 is also 2x. That means those two functions are both antiderivatives of 2x. And in fact, this is a persistent annoyance when you're doing the antiderivative, but we can always change the antiderivative by a constant, by like adding a constant. There I just added 1 to it. There's nothing special about 1. It could have been any constant that I added on. So we can always change the antiderivative by adding a constant, and we get another antiderivative. And we'll get another antiderivative. Another. All right. So in general, so I will say 2x has antiderivatives like, could have been x squared or x squared plus 1 or x squared plus 18, etc. Right? Generally speaking, we say that x squared plus c is the antiderivative, even though it's not really one thing. It's x squared plus any constant. So this is called the general antiderivative, where that c there is representative of any constant. It doesn't mean a particular number. It just means that when I take the antiderivative, it's x squared plus any other constant. All right, that's called the general antiderivative. Whereas these ones individually, these are called particular antiderivatives. Particular antiderivatives. Right? They're ones which just have a particular value for the constant in there. Yeah.
For that specific, like 2x squared, you also say x squared minus c because any constant?
Sure. Yeah, so when I say plus c, I'm imagining c could be any constant and c could be negative. So it would, yeah. You could also have minus, you could subtract constants also. So this c is allowed to be positive or negative. Yep. So that's just the language here. These individual ones are called particular antiderivatives. Usually when we're talking about antiderivatives, we will always write this one with the plus c. The effect of this is basically every time you write the antiderivative of anything, it will say plus c at the end. And I will get sort of draconian about making you remember the plus c. You will often forget to write the plus c. It usually doesn't matter, but it is important for technical reasons, and also like when you're using the antiderivative, the plus c is important. All right. Anyway, let's talk about other functions. Can you find the antiderivatives? Just like with the derivative, we're basically going to just memorize certain formulas. Like with the derivative, you just memorize the power rule. You also memorize the product rule and the quotient rule, and you can basically do whatever derivatives you want. You memorize sine and cosine, that kind of thing. So we're going to do the same thing using concerning the antiderivatives. So the antiderivative of, like, can I just write sort of a little chart here? If my original function was 2x, then the antiderivative is x squared plus c, right? What about if I change, some other function? So there are some functions when you can kind of tell what the antiderivative is. Like, for instance, 3x squared. I happen to know that that is the derivative of x cubed, right? And so the antiderivative of 3x squared is x cubed. What if I had just x squared here? Can anyone, you have to kind of guess here. What is a function, fill in the blank over here. What is a function so that when I take the derivative over here, I get x squared? Anybody? I know most of you have seen this before, some of you at least. What function can I put over here so that when you take the derivative, you get x squared? Yeah?
1/3 x cubed.
Yeah, 1/3 x cubed. Surely you mean plus c, right? I just said you will from time to time forget to put the plus c. You hope that it's not a big deal. In most cases, it's not a big deal. All right? Yeah, can you sort of see a pattern here? What if I have x to the n? Anybody know the rule? The antiderivative of x to the n? This is like a power rule for antiderivatives. There is such a thing. Yeah?
Would it be x?
You can think about what happened right here.
Okay, 1 over n x to the n plus 1.
Yes, he said 1 over n plus 1, x to the n plus 1. All right? You increase the power by 1. This is a rule worth memorizing. You increase the power by 1, and then you divide by that new increased power out front. All right? This is the opposite of the derivative power rule. The derivative power rule is you decrease the power by 1, and then you multiply by, you multiply first, and then you decrease the power, right? The power rule for the derivative says you multiply the exponent into the coefficient, and then you decrease the exponent by 1. This is the opposite. It says you increase the exponent by 1, and then you divide it into the coefficient, all right? You're doing the opposite thing. And in the opposite order. That's because everybody knows when you reverse a process, you should reverse each of the individual steps and do them in the opposite order, right? This is actually a theme, and you're going to see that same idea in other classes. The way to think about this is if you put on your socks and then put on your shoes, to undo the process, you take off the shoes first and then the socks. You got to do it in the other order, right? That's why in the derivative you multiply the coefficient and then you decrease the power. In the antiderivative, you increase the power first and then you divide the coefficient. Anyway, this is the power rule for antiderivatives. All right. And there are many other rules that are important. I want to put all the really important ones in a big chart here. And I will start with that one here. So again, I'm going to make it, those were sort of individual examples. Oops. Original function and its antiderivative. The most important rule is x to the n. The antiderivative is 1 over n plus 1, x to the n plus 1, plus c, of course. All right. This is the power rule for the antiderivative. And I would say memorize it, but like that one you're going to do over and over again. You will not have a problem memorizing that. Okay. What about, there's a few other very important rules. Here's one. How about Oh, and can I say this works just because the power rule works for any value of n. This works for any n. It works even for negative values and even for fractions. Works for any n, except there is one value of n for which this formula doesn't work. Anybody have anything to say about that? You can actually tell from looking, you don't have to know something special about this. Let me beautify this a little bit. 1 over. You can tell from looking at this formula, there is a specific value of n which could not possibly work in this formula. What do you think? Yeah, -1. This works for any n except n equals -1. It turns out there's a special rule when n is -1, which I don't want to get into today, but for any other values of n, you can use this formula. Okay, what about the next line here I want to talk about is a constant. What if I have just a constant? You could imagine, I'm going to erase this next, but what if it was just, say, the number 3? Can you make a function here whose derivative is 3? What's a function whose derivative is just 3? 3x, yeah. So to get a constant in general as the derivative, the antiderivative needs to be that constant times x, right? Because then when you take its derivative, the x part will go away and you are left with just a constant. So if I have just a constant by itself, the antiderivative is just that same constant times x, and then plus c, of course. All right. These two rules are really kind of the bedrock of most of the antiderivatives that we're going to do in this class. Although we should also talk about sine and cosine. They have nice antiderivative formulas. Cosine of x, I'll put first. So fill in the blank here. That means I am trying to think of a function over here so that when you take the derivative of this function, you get cosine. What's that function? Everybody knows. Some function, when you take its derivative, you get cosine. Somebody want to shout it? It is the sine. Yeah, the derivative of the sine is cosine. So this is the sine of x plus c. That you should definitely memorize. Just like I hope you still remember the derivative of sine is cosine, right? And what about sine over here? The antiderivative of sine x. You need a function so that when you take the derivative, you get sine. Well, the derivative of cosine is negative sine, so how would you get just sine as the answer? What are you going to say? Yeah, negative cosine is what you need over here. All right, so the antiderivative of cosine is sine, and the antiderivative of sine is negative cosine. If you're one of those people who can never keep it straight, when I take the derivative, do I get the minus sign from the sine to the cosine or the cosine to the sine? This will just confuse you even more, unfortunately. You have to remember the derivative of sine is cosine, the derivative of cosine is negative sine. And with the antiderivative, it's the other way around. The antiderivative of cosine is sine, the antiderivative of sine is negative cosine. Those can be easy to mix up. You just got to keep it straight somehow. And then there are others with the trig functions. You know, we learned about the derivatives of tangent and cotangent and all that, so I don't want to write them all down, but there are others. For example, the derivative of tangent is secant squared. That was one that, I don't know if you had that memorized, but what that means is the antiderivative of secant squared is tangent, right? Because the derivative of tan is secant squared. That means the antiderivative of secant squared is tan, all right? And I don't think we need to write all of those, but I will just say, etc. There are several other more obscure formulas for the other trig functions and antiderivative formulas involving the other trig functions, which we're not really going to use. I mean, every so often it might come up, but I would not expect you to, certainly to remember them. All right? So every derivative formula, like from those weird other trig functions that nobody really remembers, all of those formulas can be rewritten as an antiderivative formula. These ones that I wrote up there are the important ones. Antiderivative formula. Right? These ones that I wrote there are the ones that I would expect you to know. Actually, not this last one is not going to come up really, but those other ones you should have memorized. Although, like I said, we're going to do it so often that it doesn't really matter. All right. are still very simple types of functions. A single power of x, or a single constant, or a sine or a cosine, right? Really, we would like to be able to find the antiderivative of any function you can think of, any kind of combination of these things added together or multiplied or whatever. So that's what I want to talk about here. What if we have stuff added together or multiplied by a constant? Multiplied by constants. It turns out these are handled very nicely, for the same reason that the derivative works nicely when you're adding things together. If you're actually multiplying two functions, you have to use the product rule, which is a pain. But if you're just adding, you don't have to do anything special. You just add up the derivatives. The same is true for the antiderivative. So I'm going to write this as a theorem here. I'll say let f, the little f, have antiderivative, the big F, and the little g. Let's say we have two different functions and they have two different antiderivatives. Have the antiderivative, the big G. Then I'm going to say two things. First of all, the antiderivative of little f plus little g is the big F plus the big G. So all I'm saying here is if you are adding two functions together and you want to take the antiderivative, you can just take the antiderivative of each one separately and add the two answers together. There is not, you don't need any kind of special rules or special formulas. If you are adding, you can just add together the antiderivatives. If you're multiplying, you're sort of screwed. Like there isn't a good thing to do if you're multiplying in an antiderivative. In a derivative, you can use the product rule. In an antiderivative, there's something kind of like the product rule, but it's not called the product rule, and we're not going to talk about it anytime soon. All right? Anyway, this is a fact about the antiderivative if you add them together. This is also true if you are just multiplying by a constant. So it's also true that the antiderivative of, let's say, kf is k times the big F. If your function is multiplied by a constant, then the antiderivative is just the same thing multiplied by the same constant, the same antiderivative. Again, this is because the derivative is so nice when you have constants as coefficients, they just stay the same. And so the same nice fact is true of the antiderivative. All right? And so let's just do, I got 5 minutes, some very simple examples. How about find the antiderivative each time? How about if f of x is, say, 5x squared minus 7x to the 4? What's the big F of x? Basically, what you should be focused on is these powers, x squared and x to the 4. The 5, being a coefficient, will just stay the same, just like here. When I have a constant in front, it just stays as the same constant in front. And the 7, being a coefficient, will just stay the same. So it's just going to be 5 times, something here, minus 7 times something here. And then what goes inside the blanks there are the antiderivative of x squared and the antiderivative of x to the 4. And what are those? You use that power rule that I just talked about a moment ago. This thing here, right? For each of those guys. So what's it going to be? X to the x squared becomes 1/3 x cubed, and then x to the 4 becomes 1/5 x to the 5. Right? This is how we do it. If you like, you can put the coefficients together. I mean, this is usually how I'm going to write the antiderivatives, but you can write 5/3 x cubed minus 7/5 x to the 5 if you want to. Generally speaking, I don't care if you resimplify it some different way. All right? The moral of the story is if you have a bunch of stuff added together with constant coefficients, the constant coefficients will just stay like they are. You just add up the antiderivatives. How about, here's another one, a little more interesting here. 4/x squared plus root x. So I never said anything about how do you handle division, and I also didn't say anything about how you handle square roots. my suggestion would be rewrite as powers of x. For example, so I'm not writing the antiderivative, just the same thing again. I'm going to resimplify it. The square root of x, everybody knows. The square root of x you can rewrite as a power of x as x to the 1/2 power, right? So I'm going to write it that way. Can anybody rewrite the first part there, 4 divided by x squared? Rewrite that using only a power of x. What's the 4? Yeah.
X and negative 7.
Yes, so this will be 4x to the minus 2, all right? This is not my answer. That's not the antiderivative. That's just rewriting the same thing again, so that it looks like just powers of x added together with coefficients. And then, so the actual antiderivative now, the 4 stays like it is. And then what happens to x to the negative 2? You increase the power by 1. Remember, that means add 1, so it's negative 2 plus 1, which is negative 1. So the new power will be x to the minus 1. And then you divide by that same new exponent. So it will look like that. That's the negative 2 power. And then plus x to the 1/2 becomes 1/2. I add 1. I got 3/2. And then out front, I divide by 3/2, which looks like this. All right, so that's the antiderivative of this one. Yeah, if you want to, I mean, this is, oh, sorry. I'm so foolish. I forgot to put the plus c both times. Should have been plus c. Sorry about that. As I said before, you can resimplify this however you like. That, what I just wrote, is a perfectly correct answer, although some people don't like the way that looks. You could simplify it like this if you want. 1/3/2 is the same as 2/3. All right? All right, I think that will do it.